leave off? Oh, yeah. So we were talking about hydrogenation of alkenes. We've seen the reaction, but we didn't see the mechanism. Okay, so we're going to talk about the mechanism right now. Okay. Okay, so let's do an example first, just to recap here. You can do catalytic hydrogenation with a bunch of substrates. Okay, so alkene, you have a particularly weak alkene bond, not very stable. So it's going to react under the appropriate conditions. All right. So this is called Care-Dreen. All right. Okay. So if we put this under catalytic hydrogenation, in this case, we're going to use deuterium here and a platinum catalyst. And here's the solvent. So the bottom part is a solvent. So it's important to recognize like what's reacting and what's just like fluff in the reaction. This is just how it's carried out. Okay. So remember last time, if you go back to your notes, we kind of said you get both an enantiomers. Okay. So I want you to think about this structure. There's that cyclopentane ring in there. All right. So to kind of make sure we understand like what's happening, so why don't you take 10 minutes, right, on a piece of paper. I want you to predict the product and explain why it's that product. Okay, and then I'll collect it for feedback. So what happened here? So I'm going to tell you right now. It's not a racemic mixture. Only one product is preferred. Let's see if we can guess what that is. Okay, so take about 5 to 7 minutes. Write your answer and be able to explain why that is. Okay, and then I'll collect that, and then we'll go over the answer together. Okay. So I'll write right here. Only one product is formed. I'll be right back. Think about what product is formed, okay? Got it. Look up. No. Once the product here get hydrogen goes into the top face. So think of how this group here is going to influence the product. Yeah, so we're just maturing the double one. So you want to draw maturing matters. But they're going to be a specific way. When we face it up, or point it to the bottom. Yeah, with a double bond. All right. Does anyone have a guess?
Elizabeth and I put the deuterium carbon for the alkane.
All right. So what enantiomer did you draw? Are they both coming out of the page, the deuterium, or inside of the page? Or are they going in the back? Dashed? Okay, good. All right. So this wedge group right here is going to cause you some problems, and we'll talk about why. Okay, so the product you only get is actually this. So it's coming from the bottom face, so you get 98%. And remember, it's syn addition, so that's why you get both deuteriums going to the same side. All right, so you don't see any of this. You don't see any of the enantiomer. All right. Does anyone have an idea why? Okay. Yeah, so you can kind of think of steric hindrance. Okay. So what do you think the role of the catalyst is? Let's talk about that. All right. So once you've seen this picture, you can fix your answer and then just turn that into me. Okay. So here's a metal surface. Okay. So this is your metal. So let's just pretend this is our catalyst, our metal catalyst here. So what do you think the catalyst is doing with hydrogen? Well, hydrogens are going to be flying all over the place, right? So what do you think the catalyst does? Yeah, it helps it put into position so the alkene can bond to it. So it's going to do this. You're going to stick the hydrogens onto the surface. Okay. Well, sorry, let me just go back. Let's just draw a different picture because this won't make sense. Okay, so the hydrogen atoms are like right here. They are now chemically bonded to the catalyst surface, all right? So H atoms bond to metal atoms. Okay? Now the alkene comes into view. Okay, so let's just use our simplest alkene, ethene. Oh, sorry. CH2 double bonded CH2. Okay. So now let's draw a simpler view of the catalyst. So I'm going to draw a 3D shape here. All right. So the H's are sticking out still. But now the alkene has coordinated to the metal surface. So now we have our carbon-carbon bonds coordinated here. Okay. So you can kind of see that the alkene has to bond to the metal surface. So what do you think this group over here is going to... Well, since it doesn't work now. All right. It used to work. All right. So what do you think this group's going to... What do you think that group going to do when it approaches the metal surface?
The hydrogens will be attracted to the carbons.
Yeah, they'll be attracted to the carbons. Good. But why does this one only form? If the alkene has to bind to the metal surface, right? What do you think this group's going to do? Is it going to get in the way? Yeah, it's going to affect the way you interact with the metal surface. So this group has to flip over, and that's why it prefers to attach right here from the bottom face, sorry. Okay, so that group there gets in the way of the bonding. So that's why the second isomer there is not preferred, and this one is preferred. All right, so we see it has to bind there, but now what happens here is this hydrogen is going to add to this carbon, okay? And then this bond here is going to donate electrons and stick to the metal surface. So let's draw the result of that. All right, so here we could say the alkene binds, okay? First H atom transfers to carbon. So the first hydrogen will transfer to carbon. Okay. Now you're going to draw the metal surface again. So let's draw it again. So there's some grooves and edges here so the catalyst can bind to the hydrogens. Okay. So now I'm going to draw my other hydrogen, still sticking out. Okay. But now my alkene has now been saturated because it's already bound to the metal surface. Okay, and what happens here is that this methyl group that has now formed is going to be sticking out. Okay, so you see here, if I had in our example we just went over, that small triangle of the cyclopropane, that will influence which side will preferably get attacked because of steric hindrance. Okay, so now what this does is the second hydrogen is going to be grabbed here, and the electrons return to the metal, okay? And then you're going to regenerate the catalyst. So the second H transfers. Okay. Now you have the free catalyst. All right, so the catalyst is regenerated in a perfect world. It's a lot more complicated than that. So catalyst is regenerated. Okay. And here, the hydrogens have been added to the carbon double bond. And what do we know about the hydrogens? Have they been added in a trans fashion or in a cis fashion? Cis, the same face of the alkene, right? So that's why we get two enantiomers. You get two potential places for the alkene to bind. Okay, but this is not a great example because this is not chiral. But for example, this example right here, okay, that one will preferentially bind where that cyclopropyl group is sticking outward away from the metal surface. And that's why that one is preferred. You're actually going to the bottom face. So I could kind of show you what that looks like, okay? So imagine we have our metal surface here, right? All right. So your cyclohexane, it looks like this, right? Well, if this is sticking outward like this, right, this is going to interfere with the metal surface, okay? So what it has to do, it has to flip over. So we're going to do a 180 here, where now, okay, I'm going to put my double bond right there, and these are actually going backwards. Okay, so now I'm actually binding on the opposite side. So now the alkene can bind to the metal surface, okay, without any interaction with that without that second ring getting in the way. So only one isomer is preferred. So preferred conformation. All right. So during the break, just clarify your final answer here, okay? And then just explain in a few words why that one is preferred based on what I've shown you here. And then just hand me that up here during the break, okay? All right, but that's catalytic hydrogenation. Are there any questions? All right, so kind of get explain this a little bit better. Let's just watch like a video showing the overall process in real time. Okay, so I'll show that right now. All right, where is the thing? All right, alkene chemistry, hydrogenation. So let's just play the movie here. All right. So here's the metal surface. Let me just zoom out here. So the hydrogen is going to bind there, okay? So the hydrogen likes the metal. That's how hydrogenation usually works. So there's a bunch of hydrogen adhering to the surface. So that allows the alkene to, when it hits the metal, it'll immediately react, okay? So here comes the alkene. It's going to bind there, okay? And you see here now the hydrogens and the carbons are very close together. Now they can react because that double bond has been broken. So the metal serves as the place of reactivity and they get them close together. And you see here that they form, both the hydrogens go to the same phase, okay? You don't have to reproduce this mechanism, but you should be able to predict what the product is, okay? Are there any questions on that? Any questions? Catherine.
Why does the carbon bond first to the metal instead of being attracted to the hydrogen bond?
Oh, good question. So, the CC bond, is that polar or non-polar? Non-polar. What about the HH bond? Also nonpolar. That's why they don't interact, because they don't have any preference to interact. So they first have to kind of be separated. That's what the metal does. It polarizes both the hydrogen bond to separate into two hydrogen atoms. Then it polarizes the carbon-carbon double bond. So now you have some partial, I would think you would have some partial positive character because the electrons are now being attracted to the metal. So now the carbon lacks electrons. And then the hydrogen can just use its electrons to bind to that carbon atom now. Okay. All right, so let's go back to what we were doing here. So here's the notes. All right. So here, alkene product release. Okay. So we can see here that the H's has added sin. All right, so that's our first start into alkenes, okay? So now let's talk about the character of the pi bond. All right, so basic. Of pi bond. All right, so the most common reaction an alkene does is something called electrophilic addition reactions. So that's the mechanism. That's the name of the mechanism, okay? So electrophilic addition. So the alkene is a source of electrons, so it's going to add electrophiles to it, okay? So reactions. Oh, sorry. Erase that S. My verbiage is getting mixed up. Okay, so let's just draw our generic alkene here. All right, well, sorry, let's just erase that. Plus my electrophile. So it usually looks like this. You have something bonded to your nucleophile. That's electrophilic. It's usually an H, okay? And then what you get here is addition across the double bond. Of these two groups. All right, so you see here across this double bond, we have added both our electrophilic atom and the nucleophile. Okay, so we have added them both here. So you see that how those atoms split up and they added across the double bond. Okay, so we can say here the molecule E nucleophile adds across the double bond. All right, so this mechanism is going to be very similar for everything we'll show you, okay? All right. Now, before we get into this, you might say, okay, but which side does E go to, and which side does the nucleophile go to? So there's some ground rules we're going to establish here. All right, so first we have to think about regioselectivity. So remember, regioselectivity, that's like asking you, which side does my atoms add to? Does the water add to the left side of the alkene or the right side? So there's a generalization we'll make about that, okay? So regioselectivity of electrophilic addition reactions of alkenes. All right, so the first thing we should mention is Markovnikov's rule. All right, I know that sounds like a Molotov cocktail, but that's not it. All right, so Markovnikov's rule tells us, okay, when we have a double bond, that the electrophil, well, I'll just explain it right here. Okay, so the addition of a dipolar. So what do you guys think dipolar means? Close. Just think one molecule. It's like you have one molecule, right? What does it mean to have two poles? Any ideas? Well, what does dipolar sound like? We might have heard this term before. Sounds like a what? Dipole? What's a dipole? Yeah, so you're going to have a partially positive negative, partially positive part in the molecule. Okay? All right. Sorry, that should be molecule. Sorry about my writing. H nu, okay? So usually the H will be your partially positive part. Your nucleophile is your partially negative part. So the H is the electrophile. The E plus, the electrophile. All right, so remember, just E plus means electrophile. All right, the electrophile will go to the less substituted side. So the less substituted side. And by side I mean the vinyl carbon. So vinyl carbon means double bond. Okay, so a vinyl carbon is this C double bond. Okay, and the nucleophile, okay, bonds to the more substituted carbon atom. Okay, so let's do an example. So here's a common example. Hydrohalogenation of an alkene, HCl plus a vinyl alkene here, or vinyl carbon atom bonded to another vinyl carbon atom. So that's an alkene. All right, so if we draw this structure, what happens here is the RCH part, that's more substituted. So that's where my nucleophile will go, chlorine. And then the hydrogen, my electrophile, goes to the least substituted side, and that's my H. Okay? So here's my electrophile, E plus. Here's my nucleophile, Nu. So, the reason why it goes this way is much of the same as we've been talking about. The intermediate, a carbocation, is more stable at one of the positions. Okay? So let's talk about the mechanism there. All right. So, now let's try this ourselves. Okay? So let's take a few minutes and try this one. But first, are there any questions on what that means? Okay. So let's do a little exercise here. All right. So write the major organic product of this reaction. All right, so this doesn't really mean anything. 50% just means that's just the concentration of the acid. So if this acid is not very concentrated, this reaction will be very slow. Okay. So you have an acid, but you have an alkene too. So be careful. There might be what happening here? So when you have acid, you can generate a carbocation, right? But what happens generally if you generate a carbocation? Rearrangement. So you might have rearrangement in this one. Excuse me. All right. So I will write right here. Consider C plus carbocation rearrangement. All right, so let's take 5 minutes to kind of think about how this happens. So first, what's the first logical step in this reaction? You have something with a lot of electrons, a pi cloud. Remember, those are loosely held electrons, right? So what do you think happens first? Yeah, you're going to protonate one of these carbon atoms. You have to decide which one that is based on what I just taught you right here, okay? And then you're going to generate an intermediate, but might rearrange, okay? So take 5 minutes and see if you can write the correct product, okay? We saw that this specific heat, right? You're pro now. Did you get this one or no? Yeah, remember double bond here? See this double bond? It's less. This has no carbon atoms, right?
Yeah.
That has 2 hydrogens. The other one has a carbon group and 1 hydrogen. So the right side is more less substance. So you want to put the hydrogen. No, you're breaking it up. Yeah, so I would write H there. And over here. Put H there. Yeah. So where's the carbon cation?
This carbon.
Yeah, hold on, right there. Yeah, fine. And then remember, like I see a tertiary position, right? Here I just asked you to write the product, but if you can see the product, it might help you though if you know the mechanism. Oh, this pairs, remember? So this electrons are being used. Yeah, it breaks away from the carbon and forms a bond. All right. Okay, does anyone have a guess? Yes?
Maybe it would be you have an OH bonded to the carbon that also has the methyl group on it.
Okay. And then the double bond disappears, right? Yeah. So I think this is the product we started with last week in lab. So yeah, so you can make our starting material from last week by using this alkene. Okay? All right. Did anyone else get a different answer? So who got? Did anyone else get this answer? Do we agree? All right. What do you mean?
We were focusing on the
Oh, so very good. All right, let's go over it. Okay.
Yeah.
So, first things first. What's the first step? All right, good. So, you're going to treat the double bond as if it was a lone pair on, say, oxygen, okay? So, this will attack this H and protonate. So, where does the H add? So, is it going to be to the right side of the alkene or the left side? The right side. That's the least substituted position. So that's where our H is at. Okay. Now our carbocation's right here. But what's wrong with this carbocation? Is that going to be stable? No. There's a nearby adjacent position where there's a hydrogen here. So let's show these bonds here moving to the carbocation. So now we have a hydride shift, and now we have another hydrogen right here. All right. So you also have sulfate right here, hydrogen sulfate. So sulfate can be a nucleophile, but it's not a very good one. It'll just come right off. So it's a great nucleophile. Well, it's not a great nucleophile, it's a poor one. It's a very poor nucleophile, and it's a great leaving group. So that's a problem with the product. It won't stay there for very long. I've seen people write this, but I've never seen it before. Okay, so just ignore that. So what's a much better nucleophile in this reaction? OH. You have H2O. You have a lot of it. Okay, so water here is going to come around and attack your carbocation. So now we get this group here. Now let's show one of the hydrogen atoms. So do you guys remember what's the problem with oxonium ions when we have an oxygen plus ion? They're really good what? Bases or acids? Acid. So this hydrogen can just fall off like that. What usually happens is you have a solvent molecule, and that's probably just water with its lone pair, and it picks off this hydrogen, and you're going to get your alcohol here.
Couldn't we use the sulfuric acid?
Yeah, you can use that too. It's fine. All right, so generally what I like to do is I show that the solvent is picking up the hydrogen, but you can show anything that has a lone pair or a negative charge. It doesn't matter, okay? As long as it has an extra lone pair. If it doesn't have lone pairs, you can't do that, okay? So that's our product here. Okay, are there any questions about the mechanism? So very similar to alcohols. You protonate the leaving group. In this case, you don't have a leaving group though. The alkene is your leaving group. It disappears, okay? So here, the alkene. So the alkene here, quote unquote, leaves, okay? And you get a carbocation on more substituted position. All right, in this case, it's a secondary carbon atom. All right, so that's why alkenes are not very stable in acid. They tend to get protonated, okay? Yes.
Also, the hydrogen that we added after we deprotonated.
Oh, after I deprotonated?
Yeah.
Oh, you want to show me? You want me to show where is it?
Yeah, is it okay to show that?
Yeah, you can show where it is. We're talking about this step, right? Yeah. You can show it. You can just write it. I just wrote it right here. Plus H solvent. But you can show that on the side if you want. Okay. All right.
No, in the second step where you have the hydrogen in red,
Oh, that one.
Yeah.
Yes. You don't have to show it if you don't need to.
but we could.
You could if you want. If it helps you. Yes. Okay. Any other questions on? So this is adding HCl. Sorry, not HCl. Water across the double bond. Yes.
The alkene, like the carbon and alkene bond, both have like R groups on either side.
Oh, they're equivalent. You're going to get a mixture of products. Yeah. So that's the bad part. It's not very selective. All right. Okay. Well, let's just all right. So I'll just introduce this reaction before we take a little break. Okay. So now we're going to talk about our fourth reaction. Well, why is it 4? Did I skip a page, bro? OMG. Yes, I did. Okay. All right. Okay. Okay. Sorry, everyone. All right, let's just do one more example. Okay, so, all right, now let's show the mechanism of electrophilic addition. Sorry, I kind of started with my example of my exercise instead of going over the mechanism. My fault. So let's write the mechanism here. My notes were backwards. Sorry. All right, so When you have R groups around the alkene, we call this electron rich. The R groups are donating electrons to the alkene by hyperconjugation. Remember hyperconjugation? The interaction of those two carbon groups. So we say this is an electron rich alkene, okay? So how can we make this alkene electron poor? Instead of R groups, what do we put on it? Any ideas? How do we make this electron-rich alkene electron poor instead? Yeah, electronegative groups. So like carbonyls, halogens, nitro groups. That will deactivate this alkene, make it really hard to react. So that's how you can kind of tune the reactivity. All right, so what's the first step here of the mechanism? I need to add the hydrogen where? Any ideas? Less up to the side, okay? So what I like to do is, if I have a double bond and I want to clearly show where the atom is adding, I will draw an arrow from the double bond going through my carbon atom and attacking the electrophile here. So when I do that, it shows me I'm adding the hydrogen to that carbon atom I just went through. Okay, so that's another trick you could do. I learned that recently. All right, so what you get here is a carbocation intermediate. Now the polarity or the shape has changed. Now there's a carbocation in the empty p orbital. Okay. And now my other carbon has rehybridized to a tetrahedral carbon atom. Like so. Okay. Now I have the chlorine nucleophile. So what's special about this intermediate? Where can it attack? Either lobe, yes, either the top face of the p orbital or the bottom face. So it can go here or over here. So remember, just because this plus charge, I drew it in the top lobe, it's the whole, remember the orbital represents the location of the approximate location of the electron. So the already know of the orbital. So this empty orbital is plus charge in the top face or the bottom face. So it can actually go in either direction. All right? So then what you get here is you get a racemic mixture. Okay? So I'm going to just draw one enantiomer and just call it racemic, okay? So I'm going to do that. C. All right, and then plus enantiomer. To illustrate that, this is pretty much racemic, okay? All right, so let's take a little break, okay? If you have, turn in that question I asked you to write on a piece of paper. If you're going to take a little break, okay? All right, let's take 10. Yes. What's up? Yeah, so tell me hydrogen. So yeah. Okay, yeah. Yes. Yeah. If it's symmetrical, yes.
So for this one?
Yeah, see this one, there's 3 CH3 groups, so it must be bonded to a central carbon. Yeah. Or else you can't have that right? How does 9 hydrogens, how do they give you just one signal if it's not symmetrical?
Okay, and these are going to be 2 signals, which is why.
Well, no, remember that's a double. Yeah, so you actually have 1, 6, so each of these are, see where it says H? 1, 2, 3, 4, 5. So you have 6. So the peaks look like they have more signals, right? That's what the signal pattern. Remember that couple? But it's only 1. So they'll count. Yeah, that's the splitting pattern. Remember in your neighbors, the signal won't look like a singlet or one piece, it will look split. Because the hydrogen is being influenced by the magnetic fields of the neighbor. No neighbors. No adjacent hydrogen. So just think one carbon over, are there any hydrogens nearby? If it's 0, 1. The n plus 1.
So, that's why this one.
Yes, because there's no neighbors. Between any of them, nothing. Right?
So in this one,
Yeah, so n minus, signal minus 1, right? 4 minus 1, 3 neighbors. That just tells you how many hydrogens give rise to this. 2 hydrogens, C, 3 neighbors nearby. Yeah, remember that's the duration. That tells you like how many hydrogens are bonded to that specific carbon element. Okay? So these are a little too tough. Right? That's more realistic. Yeah. But these are good too. You'll be a pro. Yep. Very much. Right. Interpreting the spectrum. Yeah. You draw the. You got to draw on a paper. Yeah. Or if you
with the first problem.
Yeah, just if you.
That one, the Deuteronomy.
Yeah.
We
So
did that.
You did that one? All right. Just put both of you.
Wait, Professor Andrew, I still have a question.
Yeah, just turn that.
Professor Andrew.
Yeah.
Sorry, I thought you were referring to the alkene one.
No. All right. Anyone else? I'm gonna read it. Don't worry. As long as you attempt it, I'm pretty much sure you can do it. What's the special like today? Well, some people are just absent. Alright, well, where's the attention? How many people are missing? Yeah.
For the question, what else did you want to write?
So just write what you think the product should have been, and just explain why that worked out. You want to have the attendance?
It's over here. Wait,
You guys sign in?
Professor Andrew,
Yeah.
are we gonna get this?
Well, you get something like this, I'm sure.
Yeah.
But I think the problem is
You know what it is?
might be too guys.
Looking at everything.
Yeah, you got NH2.
I think if I did, I would
Mogi just busy, right? She had something to do. You know? No worries. I'll just check them.
Yeah.
Raven's no, some people are just sick. And Raven's has to run from backwards day, so it's probably gonna be late. If you show up on Tuesday, who's Thanksgiving, sure. I don't know, maybe. Showed it, right? Okay. Let's see. I guess you guys haven't.
these are in your stage. I'm pretty sure. And then these peaks right here is the this is in stage.
No, it's not that acidic. So it won't work that way. Yeah. Usually it helps if you have acid. Yeah. Alright guys, let's resume here. So here you get a racemic mixture. Thank you. All right. So when we react with HCl, HI, or HBr, that's called hydrohalogenation. You're adding hydrogen and a halogen to the alkene. So there's some limitations here, as we can see with the carbocation. So hydrohalogenation. Of alkene. All right. So the problem with this is that you can't decide if you have syn addition or anti-addition. And why is that? What's the intermediate? A carbocation. Remember in hydrogenation, the metal surface binded to the alkene. So if you had steric effects, you can actually direct synthesis of just one enantiomer. Well, with this group, it's kind of hard to do that because the carbocation is flat and planar like this. All right? All right, guys, let's focus in here. So we get 2 methyl groups. So let's think about this. So if you have HCl, and here's a solvent, acetic acid, CH3, CO2H. So that's acetic acid. And you get a cyclohexane as your product. But the HCl can add in a syn fashion or a anti-fashion. What I mean by anti-fashion is that the HCl is on different sides of the molecule, like this. It's supposed to be syn. So here we have a 40% mixture. You only get 40% of this, so there's complications. So not a very great reaction. So racemic, syn addition, plus the other isomer, it's not even an enantiomer of it. So here you get 18%. Also racemic mixture, so you can have the other enantiomer of this product. And this would be anti-addition. All right, so now the chlorine will add to one side, okay? But the hydrogen will add to the opposite face. So you see here, one is on the wedge bond, one is on the dash bond. So that's the anti-addition. They're on opposite sides. So that's only the start of our limitations here. The other limitation, if we have carbocations, what can they do? Yes, rearrange. So that's not good. So carbocation rearrangement. And we saw that in our example we did together right here. Okay. So here are some of the conditions I'll employ. HCl. All right, this is a solvent. CH3, NO2. So this is just a solvent. So I'll put a solvent here. Solvent. So that's nitromethane. Okay. Very good solvent for SN2 reactions, polar reactions, stuff like that. So here you can get the unrearranged product. So you get that plus rearrangement. So 40% here racemic plus the rearranged product, which looks like this. So it doesn't always go 100% to the rearranged product. But that is the major, so you would just write the major as that one. If you do write the minor product, you get like, say it was worth 5 points, right? You only get 3 points out of. No, you only get that. You get 2 points out of 5.
Do we not need to put the stereochemistry if we're writing about it?
Yeah, don't put it. It's racemic. And then this one's not stereocenter, so you don't have to put anything. So that's the only product you get. All right, so guys, if there's no stereocenter, don't put racemic. I have to take a point off for that, so don't put that, okay? Unless there's there's a obvious stereocenter, and I'll show you that this one is our stereocenter, right? Whereas in our other product, there's none. All right, so that's our second reaction here. Syn and anti-addition of HX across the double bond. All right, so you get 2 products. All right, so now we didn't talk about water, so I'll go in more detail about water because we just did that example. So I'll elaborate over that. So our third reaction here for alkenes, electrophilic addition of H2O. All right, so it can be water, it can be an alcohol. You'll get similar reactivity, similar product patterns here. Okay, so the case for this one, you need an acid catalyst. So acid catalyzed hydration. All right, so this is historically how we make alcohols in industry, using it for, food, brewing, fermentation, ethanol fermentation, fuels. So that's how we get ethanol. We take an alkene and we basically install an oxygen atom in there, and that's how we do it on a bulk scale. Okay. So, because these guys are actually pretty cheap from fossil fuels and cracking of oil, although it's not very, very friendly. Okay, so remember we had 50% H2O, H2SO4. So basically, what I think is happening here is that you take a sulfuric acid solution and you dilute it by half with water. Okay, so this here we get the alcohol, and it's only one product, so that's pretty good. All right, so that's a pretty good thing to have. There's no rearrangement, so that's pretty good. So let's talk about the mechanism one more time, just to reiterate this. And you can see some patterns here. You're going to protonate first to generate what? Yes, carbocation. So let's draw our, oops, my bad. There should be an oxygen here. Okay. So I'm going to go through this bond here to illustrate that it's attaching the less substituted side, going to the less substituted side, okay? All right, so bisulfate is our byproduct. Okay. Then we get the carbocation. So I've added that H there. My carbocation is on the central carbon atom. All right, what's the next step? Remember, I have water still in this reaction. So what attacks the carbocation? The water or the bisulfate? Yes, so the water will lead you directly to the product, so you should probably use the water. All right, and this is analogous. So you might think this doesn't happen in natural biology, but it does. You're just using enzymes to help you get this reaction forward. So you don't have sulfuric acid. All right, but you have an enzyme that binds the alkene and, a biological version of the alkene, and it converts as hydration in the body. Okay, so that's how it kind of gets rid of metabolites in your system, like after digestion and all that. All right, so now we draw the product here. So remember, just follow the arrows. We have a bond to water now. And you could show the hydrogen atoms to illustrate that, okay, well, this is a positively charged oxygen, so that's not going to be very stable. So what's the very last step we do here? Deprotonation. All right, so since there's a lot of water, you can use water or bisulfate. It doesn't matter. I'm going to show water this time. And what we get here is H3O+. So my acid has been regenerated to go again. And that's good for chemistry because you can recycle the acid, hopefully. Hopefully it doesn't degrade. And you get the alcohol as your final product there. All right, so an alkene, water, acid, are going to get out the alcohol at the more substituted position. So you're going to look at the carbon atoms of the alkene and This is where the nucleophile will go. This is where the electrophile will go. Okay, least substituted position. Okay, are there any questions about this? So let's sum it up. Electrophilic addition, adding electrophile part of a substance and the nucleophilic part across a double bond. The least substituted side gets the electrophilic atom. The more substituted side gets the nucleophilic atom. Okay? All right. Yes.
Instead of water, we can also use the soluble phase.
Yes, you can do
And
that.
we also do the solvent.
Yeah, it doesn't matter. Yeah, if you don't, you can just write solvent and just put a lone pair on it. That just tells me you know where it goes. Yeah. So it doesn't matter as long as you don't you just don't say goes to the alcohol. That's fine with me. You should show how it loses that hydrogen. All right, so we're going to see this trend, electrophilic addition to the alkene. The only difference is for each different reaction, you're going to get a different reagent, okay? So now let's talk about, we talked about addition here. We have two problems, rearrangement, and we don't have exclusively syn or anti-addition with strong acids and with water. We don't have that control, but there is a way to do that, okay? So the next thing we'll talk about is how to avoid rearrangement. So how to avoid rearrangements. No carbocation intermediates. All right, reaction number 4. So this is a reaction called Oxymercuration. So unfortunately, I don't think this method is now commonly used because of how toxic mercury is and how much of a pain it is to deal with to dispose of it. Okay, but nonetheless, mercury has its place in chemistry, very valuable. All right, so what this does, you're going to add a mercury group, and then you're going to get rid of it in the subsequent step. So this reaction has 2 steps. So you may see it written all at once or stepwise, like on a quiz, okay? All right, so the first step here is you're going to take mercury acetate. So let me just draw that. So you have 2 acetate groups with mercury. So that's mercury acetate. So mercury here, and then acetate groups bound to the mercury. So mercury is actually in the 2+ state here. All right, and then, so that's just an intermediate. The other thing that's adding is H2O. And then your solvent here is THF. So you need an organic solvent to dissolve everything. All right, the second step, we kind of seen these reagents before. You're going to reduce the mercury and add a hydrogen atom to get rid of it. So sodium borohydride, and so this is catalyzed in base. So there's basic conditions, sodium hydroxide and water. All right, so what you get here is you just get one product and there's no rearrangement, so that's pretty good. So no rearrangements. All right, so it looks very similar to what we did with water. Add the H to the right side and add the OH to the to the more substituted side. The group next to the tert-butyl group, right? So that's good. No rearrangements there. So this can happen so you might see this on homework. This might happen in a straightforward fashion, and this also might happen in a circular fashion where the final product is a ring. All right, so you also have intramolecular oxymercuration. All right, so alcohols. Remember, we've just been using water, but alcohols work fine too. You can use them as a nucleophile. They react as a nucleophile. All right, now I'm going to abbreviate mercury acetate, Hg. All right, so remember how we wrote acetate? C2H3O2 minus. We don't have to write that anymore. We could just abbreviate like this, OAC. Okay, so AC means acetyl group, acetate. So OAC is acetate. Okay, so we have two of those groups here. And then you still have water, THF. So that's your solvent system. Water is actually your nucleophile. No, actually, is it? No, it's not. It's just the solvent. Okay? And I'll explain why. All right, so sodium borohydride, sodium hydroxide, H2O. Okay, so instead of forming an alcohol, your OH right here is going to react intramolecularly. So what you have here is a ring. All right, sorry, I drew too many carbon atoms. So this is also racemic. So let's write the CH3 group right here. One, two, three, 4, 5, 6. So see, the oxygen here came around and attacked this group. Okay, so that's how the ring formed. So the water here doesn't actually do anything. Usually it will attack and you'll get your alcohol, but it doesn't do that in this case. So you can have some interesting reactivity here. All right, so that's good. We got the reaction, but how does it actually work? Okay, so this one is going to be a doozy. All right, so stick with me. All right, let's talk about the mechanism. But are there any questions on the details of the reagents here? So you still have the same thing happening. You're getting added across the bond H and an oxygen nucleophile. Okay? But let's talk about the mechanism now. All right, the mechanism, as you can imagine, if there's no rearrangements, there's no carbocation intermediate. It's actually a different intermediate. All right, so I'm going to abbreviate this into steps. So step 1 is called oxymercuration. All right, so the very first thing that happens is your mercury acetate is going to react in some ways. All right, so here's mercury So the mercury acetate in solution is not going to be very dissociated into ions because you have an organic solvent. Okay? So what happens here is one of the acetate groups will leave. Okay? And then here, what happens here, water will help hydrolyze this bond. So water is actually going to cleave this bond and give you a free acetate group. So the water also helps you free up the acetate. Okay, and then you're going to have a mercury atom here. Well, it's still attached to one of the acetates. All right, so this is actually your reactive species right here. Okay, so what's going to happen here? So let's just draw a alkene. We'll just draw the one we did for the first example.
Is this all still step one?
Yes. So mercury is still going to have some valence electrons. So its valence electrons are going to add into the double bond. All right, so stick with me here. So this lone pair, I'm going to circle it. It's going to come in and attack. Oops, sorry. It's going to attack this carbon. All right, because if I protonated this double bond, that's where the positive charge is most likely going to be. All right, and then this double bond right here is going to bond to the mercury. All in one step. So they come together and form this intermediate structure. Okay? So this is going to look really weird, but it looks like this. CH, CH2. So we have a cyclic mercury intermediate. Well, this looks a lot like what we saw before. What kind of ether? Epoxide. So you form a reactive intermediate, no carbocation formed, remember? And you can open up the ring regioselectively. All right, so, well, this one, remember, there's a bigger partially positive charge here, right? So way more partially positive, only slightly partially positive on the more hindered side, less hindered side. So water here, being a weak nucleophile, prefers to attack. So you can kind of think, oh wait, my epoxide, just think this out as epoxide. Remember my epoxide, remember when it was protonated? Which side did we attack preferentially? The more substitute, right? So the more hindered side. And that's because the partially positive charge here, this bond is partially broken here. All right, so this bond is actually longer here. So what does water do? It's going to attack at this position. Okay, and this will break open. So you don't get any carbocations and no rearrangements, okay? So let's draw the product on this side. All right, so now we have a protonated water, and what's the last step? Yes, deprotonation to furnish the alcohol. All right, so we get H3O plus. Plus this structure. All right, that's step one. The mercury's still there though. So the second step, you get rid of the mercury. All right, so they actually don't show you this mechanism in the textbooks, but it is known, and I'll show you what it is. All right, so let's go over the steps one more time. The mercury inserts itself into the double bond by forming an epoxide-like intermediate. So that's a common reactive intermediate. This three-membered ring structure, very reactive. So it's usually an intermediate. And then the water here, since you have a protonated atom in the ring, one of the side is longer than the other, much weaker based on how much partial positive charge can build up in the transition state, like when we went over epoxides. Okay? So you're going to attack the more hindered side here. All right, any questions on the details of the mechanism? All right, maybe a candidate for the mechanism, not on this exam though, maybe the final, but not this upcoming exam, okay? All right, step 2. Demercuration. All right, what does demercuration sound like? Yeah, if deprotonation is removal of what? Hydrogen from a molecule, then demercuration is probably removal of mercury. All right, so this mechanism is special in the sense that it operates through a radical pathway. Oh, but don't worry, I won't ask you to reproduce this one, okay? It's not even in the book, so. All right, so remember the reagents in the second step? What was the reagent in the second step? What's the very first reagent in step 2? Yes, so remember that's a source of H atom, right? So, and hydrogen anion. So what happens here is the H from the borohydride part of the molecule will donate to mercury. All right, so let's grab this bond and we're going to have it attack the mercury atom here. All right, when you do this, it's an SN2-like fashion, so the acetate will leave, okay? So the mercury is going to be given a hydrogen atom. All right, let's write the result of this step. All right, so surprisingly, the H of the alcohol doesn't get attacked. So you can kind of think of the mercury is much more electropositive than the hydrogen, so it accepts electrons better, okay? Just like metals usually do. They're electron acceptors. Okay, so now you're going to be given this mercury bonded to a hydrogen atom. All right. So what happens here now, they actually proved this in the lab in research. So what happens is this bond is very weak. So this mercury bond now is very weak because there's no acetate there. So now this will split up homolytically. So you're going to get one electron from the mercury onto the mercury, and one electron, a radical, is going to form on the carbon atom. So the byproducts here are borane, BH3, plus sodium acetate. All right. And then what this gives you is this intermediate. So this is why this reaction is a pain. So you get actually a primary radical, so that's kind of surprising, but what you have here is the mercury with a single electron and a hydrogen bond. So remember, if you have two radical species, very unstable. So what this is going to do is this is going to free up elemental mercury. So you're going to get one electron here. And then this bond with the H is going to combine with this radical from the carbon. And you're going to form a CH bond to that carbon group. So here you get mercury liquid. So you get out liquid mercury, atomic mercury. That's why it's problematic. And then what you get here is you get the final alcohol product. So the mechanism is not as straightforward as people might think, but you're not responsible for this one, okay? So that's how the alcohol forms. In the textbook, they just tell you that, oh, the mercury group falls off and it's replaced by a hydrogen, okay? But in reality, it's a radical mechanism. So here I would say not responsible to reproduce on exam or quiz, okay? But that's how it works. All right. Give a few minute or two to finish writing. But any questions about that mechanism? So when I was studying this, I didn't know what the mechanism was, like when I was a student. So it always bugged me until I found out it was actually radical mechanism. Okay. So that's how demercuration works. So the highlights here, you get the expected Markovnikov product. The OH is on the more substituted carbon atom of the alkene, gets added there, and then you don't have any rearrangements, and you don't have any issues with the selectivity. Okay. And usually here, you get both, well, it's anti-addition, really, because you look at the intermediate here, you're attacking from the opposite side. So what you're really doing, well, actually, this step is anti-addition, right? So this is backside attack. So but when the hydrogen adds back on, it can occur from either face. So if you have a stereocenter there, it's going to cause problems. But in this case, it'll probably be, what I'll show you, the ones I'll give you or expect of you, is that you should just know that this step occurs with inversion if there was a stereocenter there. And then it occurs from the opposite face of the mercury. But what can you do with the mercury? Which sides can it attack from? If we look at this step, if we look at right here, right? The alkene is planar, so the mercury can come from which side? Either side. So you get still racemic mixture. So this guy should still be considered racemic. Okay, that's why I drew this. So it's all right here, racemic. Okay, any questions about oxymercuration-demercuration? So that's a way to avoid rearrangements. And it follows Markovnikov addition. Okay. All right, well, we'll have time to just mention this one, but we'll continue this on Tuesday, okay? So anti-Markovnikov. So what do you think anti-Markovnikov means? Any idea? Well, Markovnikov, let's say, go ahead. What do you guys think anti-Markovnikov means? Yeah, so it's flipped. Right, good. So a way to do opposite selectivity, opposite regioselectivity, you do a hydroboration oxidation, okay? So here's our fifth reaction of alkenes. So what happens here is that you have an alkene, okay, let's use the one we have been using, this tert-butyl substituted terminal alkene. All right. So one, you would use borane, BH3, THF. Okay? And then the second step is the oxidation step. So hydrogen peroxide, that's a common oxidant. That's what I studied in grad school. I used reactions that use H2O2. And then water here is just, so you activate the peroxide by using base. Okay? It's not very stable in base. So what you get here is just the opposite selectivity. The double bond disappears. Okay? So what you get here is CH2, CH2, OH, oops, my bad. All right, so H goes to more substituted alkene carbon. And where does the carbon go? Where does the OH go? To which side? The less substituted. So we flip the selectivity. So that's one way you could do it. Okay? It's, less substituted. All right. So now we have pretty much two ways now we can avoid rearrangements. All right, so now you have enough knowledge now to kind of attempt the homework. So some of the homework questions, there's a lot for nomenclature. It covers everything, nomenclature, reactivity, and reactions of alkenes. So you can get started on some of those, okay? All right, I'll see you guys in the lab. Thanks.